Welcome everyone to today's webinar, Virtual Reality Optics, Present and Future, hosted by Photonics Media. I'm Joel Williams, Associate Editor at Photonics Media. I would like to introduce today's presenter, Dr. Pablo Benitez, co-founder and CTO of Limbac, and professor at the Technical University of Madrid, Spain, where he leads the Optical Engineering Group. In this webinar, he will present solutions for VR optics in the market and introduce additional challenges to be tackled in next generation designs. If you have any technical issues during the webinar, please log out and log back in again to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation today. So if you have a colleague that couldn't join us, please let them know that this recording will be available. We encourage you to ask questions at any time during the presentation. You can type your question or comment in the chat box on your screen, and we will respond to as many as possible during the Q&A. Now, with nothing further, I would like to introduce our speaker, Dr. Pablo Benitez. Welcome, Dr. Benitez.
Hello, everybody. Well, hi, everyone, and thanks all for calling in. And I would like to thank you also, Photonics Media, for inviting me to present here today to talk about optics for virtual reality. I have been working in this area in the last years, and we have founded Limbac, which is an IP company focused on developing extreme performance optics for virtual reality and augmented reality, which is a spin-off of the Technical University of Madrid. And virtual reality is considered to be a new platform for human-computer interaction, but the concept is not that new. And I was really amazed the first time I saw this patent of 1960 showing a stereoscopic television apparatus for being head-mounted. Or also the developments in the 90s, like this one of NASA, resembles very much the most present headsets. However, of course, the performance of those devices are very different from today's because mainly three dramatic improvements in three technologies. The first one is the computer power. So the capacity of our, for instance, cell phones that we have in our pockets, if many orders of magnitude bigger than that of the first computer with RAM that is shown there and that weighed about 10 tons. The second technology is the sensors to track our head, our eyes, our body, or to map the rooms. And the third one is the displays, which has also improved dramatically many aspects since those times, and also, of course, in cost. I'm going to discuss about the main challenges in VR, whose solution is expected to come from the optics, which is, in my opinion, the fourth technology that will have a dramatic improvement. So there are several features in a VR headset that should be optimized. First, the resolution, which is still rather low, and we can see the pixelation, which is particularly critical when trying to recognize faces or reading small text. Secondly, the headsets are quite bulky, which make them uncomfortable for long periods of time of use. The field of view should be large enough to have an immersive experience, and it will be also interesting to have a high transmission efficiency of the optics, particularly if the headset is going to be working standalone. There are also other challenges, like, for instance, the mismatch between the accommodation versions or the introduction on the correction of eye prescription in the headsets, or providing a very large eye box to the user. And let's consider or show here the basic design that is used nowadays. It's basically a rotational symmetric lens composed by two aspherical surfaces that are going to project the image on a display towards our eye, creating a virtual image at a given distance, for instance, 2 meters, and our eye will accommodate to that plane. On the display, we will have an image that will basically use the inscribed circle into the display. And if we take the 4 parameters that we highlighted before, we would say that this basic design is very efficient. The field of view is okay, is let's say between 90 and 100 degrees typically, but the depth and the resolution are still not that great. This number of resolution is obtained assuming a display of about 2K by 2K, which is what we have available, let's say, this year. The definition of the depth in this presentation is taken from the surface closest to the eye to the display. There is one variation of this design that is very extended in the use, which is to use that the internal surface is a Fresnel type 1. Fresnel surface is made of steps, it's a stagger structure that allows to reduce the weight and also a bit the depth that is not reflected here. And but the presence of those tips and inactive facets makes that in very high contrast you can see some artifacts in the form of rings in the image. I mentioned before that this field of view of, let's say, 90 degrees is sufficient to get good immersion, but is definitely smaller than when we can see normally, because our human vision system is able to capture up to, let's say, 200 degrees field of view horizontally. And you could apply also that basic design to this field of view, but you will do that at the expense of making the headset even bulkier. The field of view is usually measured from the rims of the lens towards the pupil, to the center of the pupil when the pupil is looking frontwards. And the lens should illuminate not only that pupil, but the larger area. And the reason for that is because you need to accommodate the eye rotations without losing the image, or the eyeball shifts associated to certain tolerances or the different IPDs of users. Oh. This makes that usually we talk about the eye box, which is like a large pupil that is calculated taking into account those expected eyeball shifts and rotations. Of course, the eye box concept is in reality a 3D one, so you have also an eye box definition for performance of the device in the zeta direction. So let's start exploring the resolution limits. An ideal headset should be such that we can see the virtual reality in the same way we are looking at the normal reality. And for that, we will need the resolution of that headset to reach the human eye resolution, which is 60 pixels per degree or 30 cycles per degree, typically. So to understand what we're talking about, we can imagine that we are watching a TV that that is also, let's say, 100 degree wide at 2 meters. And the diagonal that we will need to support or subtend that angle correspond to more than 200 inches. So the question is, for this TV, how many pixels will we need in order to reach the 60 ppd that we mentioned before? That calculation coincides with the classical distortion-free law of optics, which is the tangent law, also called rectilinear mapping. And that gives that you will need, for a round field of view of 100 degree, like an 8K by 8K display. In reality, conventional or the classical solution of VR usually have some distortion. Is common in wide-angle lenses. So in the mapping that they produce is closer to a linear mapping that gives a simpler calculation of the number of pixels needed. So you just have to multiply the 100 degrees by the 60 pixels per degree that you want to get that. In that case, you will still need 6K by 6K display to achieve that. These numbers are very, very high. And you may have seen in different public announcements the very good achievements that are being obtained at lab level with very high pixel count displays, very high PPDs. They are still not ready for mass production, so that's something that takes time, and it's very likely that it's going to take maybe 5 or more years to get those very high total pixel count situation. What we have today available, not now, but in the next, let's say, 2-3 years, is based on basically 2 families of displays technologies. One is the micro displays, either OLED or general COS could be used, which have very high pixel density, but rather a small diagonal pitch, compared to the other family, which is the one of the mobile type displays, which are larger in diagonal with smaller pixel densities. Both are manufactured in very different processes. So the first OLED micro displays have a monocrystalline backplane technology and is processed using CMOS type approaches, while the mobile phones are made more in a thin film type approach. In terms of the total number of pixels, both technologies are competing, let's say. And then the first headsets used to have per eye a display of 1K by 1K. Now we are getting close to the 2K by 2K in mass production and available in the market. And probably in 2 years from now, we will start seeing displays of 4K by 4K. So the question is, using these displays, what can we do better? Well, before, just to mention that there are other display technologies coming, like, let's say, for instance, holographic displays or laser scanning or micro LEDs, but they are still in the path. I mean, it will take time still. So as I was saying, what can we do to do better? So we certainly can improve the conventional design, and for doing that, we will need to take into account how human vision works to be able to fool the user. So our eye is basically an optical system that is projecting the light from the outside into the sensor, which is the retina. And the retina has 2 types of sensors, the rods and the cones. And the cones are the ones which are responsible for the color vision and the high resolution. But these 2 types of sensors are very unevenly distributed over the retina. So there is a part of the retina called the fovea that has basically only cones and in a very high density that allows that is going to allow to have very high resolution. But far from that, there are very few cones. As a consequence, if you measure the visual acuity, you can see that in the gazing direction, which is this 0 angle here, associated to the gazing angle from the gazing direction, you get a very high visual acuity. But when you go away from that, so a peripheral angle different from 0, what happens is that your resolution is very low. You can check this just putting a text in front of you and gazing to a different direction. If you gaze to another direction, you really can't read. But we have the impression that we see well everywhere. And the reason for that is because we are continuously rotating our eyes. In reality, those rotations are not that wide. The statistic says that 85% of our rotations occur within only a 30-degree full angle field of view. So this is also important information to take into account. So let's see how different authors has approached how to use this in favor to increase the resolution of virtual reality. And for instance, Apple proposed a what it was called a kind of a foveated display with a very high resolution and using eye tracking. But in order not to address the full display as the full resolution, with the eye tracking, you could know what part of the display was being gazed through the lens, and then that part of the display could be addressed in high resolution and gradually decreasing the resolution of the other parts to avoid the computer calculations that were needed. Other way to approach this related was proposed by Barrio, in which you can use, in these cases, the two eyes are drawn here, but assume only this one on the right. You can use also in this case, using two displays, which is a dual display option, in which this is a background display to generate the overall field of view. But again, with a gaze tracking, since you know where the user is gazing, you can project, in this case, an insert image in order to put high resolution only where it's being gazed. And these other three cases, also proposed by Barrio or Microsoft or Oculus Facebook, are three options that don't need to have the eye tracking, because they also use two displays. But in this case, what it's doing is to put an insert in the region where it's normally gazed. So you have a wide field of view in one display, and the central part of the field of view, you have a higher resolution virtual image because of the second display. The first commercial product using two displays headsets has been released by Barrio, which is a high-end headset which provides over 60 pixels per degree, so the human resolution, in the high resolution insert in the scene, using the approach that we show in the slide before. In Limbach, we have been developing our virtual reality technology that we call Thin Eyes, and in particular, we have developed one technology that we call passive foveal super resolution optics. We say passive because we don't need eye tracking to apply it, and it's based on two main features. The first one is that we use a strong variable magnification to make the pixels denser where they are normally gazed and coarser in the peripheral regions. So we are changing the fact that the display itself is uniformly spaced in pixels, but that's the actual display, and through the optics, we are changing that pixel distribution in the scene. And the second key feature is that our design assures the pixels of the VR scene are perfectly imaged only when it's needed. That is, when the eye is directly gazing. So imagine what you see here on the left is that we have turned on this pixel of the display, that the eye is projecting in this direction. So this is the direction of the pixel in the VR scene. And this eye is gazing it. So in the eye resolution curve, as a function of the peripheral angle, this means that we are here. So the eye have a very high acuity. These rays are being focused onto the fovea. And then what happens is that the eye is probably going to be able even to resolve the pixels. And we are going to be limited in what we see, but what is called the Nyquist frequency of the VR pixels, which is the maximum frequency that can be represented by that display. It corresponds to putting alternating black and white bars on the display. But what happens when we rotate our eye and look frontwards? That same pixel that was lit in this direction is now seen by the eye in a peripheral position. So the eye is looking frontwards, and there is a peripheral angle. So these rays are not hitting the fovea anymore, but the peripheral retina. And then what we have to achieve is that our resolution is better than only that one, not more. You can see this in a specific design curves for a given design, in which here on the left, we show the modulation transfer function, which is used to measure the image quality for a given point of the virtual reality, which is located at 50 degrees of axis, when it's directly gazed. So when it's directly gazed, we have to resolve the Nyquist frequency of the pixels, which in this example was this value, and we need the MTF to be with a high value, which is shown here. But when the eye is looking frontwards, this particular lens was creating this kind of bad MTFs. But what happens is that in this situation, the peripheral angle is 50 degrees. And then what we have to resolve is not the Nyquist frequency, but a much smaller one. And in fact, this MTF is as good as the other when we consider what the eye can resolve in that position. So this is what we do with our technology. And particularly, as I mentioned, we do this without the need of using eye tracking. This is an example of a dual lens design featuring this passive foveated super resolution. And this is the comparison with a conventional lens. It stays at high efficiency, and we are able to increase the resolution close to 50%, so from 20 ppd to 29 ppd, just by changing the optics with the same display. These are two images directly shot on the left through the conventional lens and on the right through our lens. And this is a zoom version of a small text, and you can see the increase in resolution. And both lenses have all the other parameters the same field of view, same display, same eye relief, etc. So let's continue now exploring the size limits. I'm going to be representing the depth in this axis. Just to avoid confusions, in this chart is put depth to the -1 because I want the good things to be away from the origin. But in the labels, I will be using, as I used before also, I will remove the -1 just to know that, not to make it confusing. So regarding the size, we're going to be discussing about two technologies, one they call pancake and the other one multichannel, which are architectures that are folded and made in arrays. We're going to start with the pancake, which is the original idea is an old idea from La Russa in the 60s that basically was replacing the two aspheric surfaces that we mentioned before by two mirrors in order to make a long focal length in a short distance. And if you just put two mirrors, of course, it doesn't work because you are completely blocking your sight, is full shading. But the trick that La Russa invented was to use polarized light, and with the use of a reflective polarizer and quads wave plates, being able to make that the light goes in the way that is drawn there. One drawback of this type of approach is that for it to work, you need to use a beam splitter, a 50% mirror. That has to be used twice, so the light goes through it in transmission and is reflected later. So the transmission efficiency of this architecture is below 25% by theory, let's say, for the case of polarized emitters like LCDs, or less than 12% for unpolarized emitters like in principle could be OLEDs. There is a second technological issue, which is very important, that you need very low birefringence materials because this device is very sensitive to polarization. And this was something that in the past was only possible to be done with glass, and in fact not molded glass, but grind and polished ones. And but now it's becoming available to have them in plastic, with the capability of making, let's say, more spheres and the reduction in waste and cost. So how pancake compares with the conventional design in these 4 parameters? So it's much more compact, so the thickness is reduced dramatically. and the efficiency is low, as we mentioned, and the other parameters remain the same. Over these last years, you may have seen in the press different pancake prototypes that have been shown around by different companies, some of them using micro displays, some other uses large area non-crystalline backplane displays like the mobile phones with different field of views. Some of them are smaller and some are bigger. And this last year has been the first release of a commercial product based on Pancake by Huawei. This is a very compact design of 90 degrees field of view using a 1600 by 1600 pixels per eye. And this specific design includes in it the prescription correction that I mentioned before, in particular for myopia, up to 7 diopters. So you don't need to use the glasses with it. In Limbac, we have applied our passive foveal super resolution to this pancake architecture. And with that, we call the super pancake, with the objective to increase the resolution by means of what we explained before. And this is an example showing the increase from 20 to 27 pixels per degree, just changing the lenses, the shape of the lenses, but not changing the display or any other element in the system. Well, yeah, going back to the pancakes, just one more option that was recently disclosed by Facebook Reality Labs, that is using, instead of the aspheric surfaces, using volume holograms. This allows to break the condition on the shape of the surfaces, making the deflection based in the holographic principles. So you can have, let's say, flat optics in order to make the roll. So this is a device whose thickness is very small, is very impressive, with 93 degrees field of view and 12 ppds, as reported using 1100 by 1100 pixels per eye, and is limited by the display, not limited by the optics. So this is a very interesting approach, which has still challenges to overcome, but I'm sure we will ahead of it in the future. So let's go to the other family of optics we're going to use to explore the size limits. The multichannel is a technique that is inspired in the eyes of the insects, and it has been used in optics over the years in different applications, but in particular in HMD, in what has been called tile displays that use multiple displays and lenses arranged around it. This has been used also to have a very wide field of view headset, for instance, with 200 degrees. In this case, using lenses, 2-channel lenses for the front direction and for the side direction, but the size of the headset is not that small. I'm going to talk more about the reduction in size that is possible with the multi-channels. So what's the basic idea of a multi-channel device? Assume that you have a conventional lens that is projecting the light from that display at that distance. And this lens has a focal length that is slightly bigger than this lens to display distance. So if you replace that lens with 2 lenses with half the focal length, you can get the display closer by half approximately, and with the 2 lenses you are covering the same field of view. So this is the basic idea, and the problem as it is that it has is that if you use the same rotational symmetric lenses that we were using before, it's not going to perform very well, because these lenses are working off axis and the optical performance is much poorer than on axis. And then at Limbac, we have been working intensively in these years for developing freeform multi-channel optics. Freeform are optical surfaces which can be bended in the 2 dimensions so they don't rely on their rotational symmetry. And this extra degrees of freedom allows to get a much better imaging quality to make that everywhere you gaze in the field of view, you see the image sharp. We apply in our techniques not only a freeform multi-channel, but also the passive foveated super resolution technique to each one of the channels, as we discussed before. So this is an example of a prototype we developed within the European project LOMID that achieved nearly 25 pixels per degree, merging the image from 2 microdisplays on the perfectly into the eyes. So it has this freeform two-folded lens, and each one of the displays has an additional cemented doublet. This is a two-material element for color correction, and additionally, in the surface, we were using a diffractive kinoform surface. This type of diffractive surface, also called blaze grating, is a Fresnel type lens structure, but that have the condition that the facet height is approximately half the wavelength. In that way, there is a constructive interference from facet to facet that allows that the chromatic behavior of this surface is just opposite to that of refraction, so you can provide additional color correction. So the combination of the two things were used to make a good color correction of this device that was working all of it by refraction, and the pixel size on the displays was very small, and therefore it was needed for getting good quality. If with the same number of channels you would like to get it even to a more compact device, we at Lindbach had developed what we call a light folding multi-channel system, closely, short nickname as Clover, which is the one shown here behind, in which the light suffers 2 reflections before going to the eye in these prisms. These are fully free-form devices, and it can be seen as related to the pancake in the sense that we are also using 2 reflections to make a long focal distance in a short depth, but we are opening a refractive surface here, so we don't have to go through the mirror twice. So this device is very efficient, not like the pancake, and can be also, and it's also quite short. The reduction in size is very much, not as much as the pancake, but close to it. You may be thinking on how in a multi-channel device you can compose the images in order to make things be seen well. And the way to do it is as follows. You have to put an image on the display, which is segmented into 4 sectors. So each one of the sectors is going to go through each one of the 4 channels in this case to create this virtual image. And this is a function that is static. What I mean is just pre-calculated, and is put in the shader of the in the rendering engine in the same way that you put the distortion correction with a conventional lens. And in one case or the other, the only difference is that in the rotational symmetric lens, you have the coefficients for a one-dimensional function, and here you have, apart from the 4 segmentations, a 2-variable function to define the distortion correction. And you can see this working in this video. So this is the image seen through this 4-fold lens, and this is the image on the display that you see on the left. But here, when you get for the user, it doesn't distinguish. There are 4 images on the display. It's just perfectly blended. We have been working also in an advanced version of the Clover using pupil tracking. If you follow the pupil, what you can make is a dynamic adjustment of the different sectors that this allows to diminish the area of pixels which is duplicated in the 2 images. As a consequence, using pupil tracking, you can increase the resolution of this 4-channel device by 20%, overpassing the one of conventional lenses with the same rest of parameters like the field of view. As I said, we still maintain a very high efficiency. This technology, the collaborative with pupil tracking, is being integrated by the French company Lynx into a mixed reality headset. This device is going to be using video pass-through for the mixed reality. So cameras in here will be capturing the reality and overlapping it with the virtual objects. And the system itself can be used for both virtual reality, covering the sides, or for mixed reality, just with a flip up structure, as can be seen there. Well, if we want to go further in multi-channeling, of course you can do it. You can put these 4 channels to reduce further the depth. But what you can think it's happening is that now, to represent this direction of the field of view, so this point of the virtual reality, you need to lead 4 pixels that gives to a loss of resolution due to redundancy. And that's certainly something that can happen. This type of concept was developed to the stream by Landman and Lübke at NVIDIA years ago to show that an extremely thin device could be built for virtual reality in this proof of concept using off-the-shelf components, which is extremely compact solution. This solution had still a low resolution in the image, only maybe about 5 ppd, due to the redundancy I mentioned, and also to the fact that this particular device was developed to produce what is called a light field, solving the divergence accommodation problem. And we will come back to this solution later. Well, we have been working in the last 2 years in a new technology at Limbach, new thin ice technology that we call Trenza, that is a mini lens based technology that is trying to solve the problems of low resolution of classical mini lens arrays. And the parameters that we are targeting in this technology are the ones shown here with a convenient display to be used. This display is different. And then we are targeting to achieve 100° and 30 ppd with a very, very compact system of only 8 millimeters. And this technology is based on 3 key elements. First, we use intensively freeforms in the design. We incorporate also the passive foveated super resolution that we introduced before in order to increase the resolution with respect to a conventional option, and also adapt the resolution to the gazing and non-gazing situations. And third, we use pixel interlacing, which is a controlled projection of display pixels through the different lens channels to remove redundancy and increase the VR image resolution dramatically. So Limbach is participating in an European project called Fabulous, which is a consortium of many European companies and public research institutions to create a pilot line to manufacture mini and micro optics with a variety of technologies. Trenza has been selected as a use case to check and challenge the pilot line that has been developed. And this is an example of one Trenza array. These are the 2 sides, which shows the fully free-form lenses with 8-fold symmetry that is going to be manufactured within this Fabulous project. We're in the first phases of it. So this is the front view of one of the sides, and this is the mold for making the lenses later that has been manufactured by one of the partners in the project, the originator, which is a Belgian company called UPMT, that has done an excellent work producing a surface profile error, which is extremely low, below 100 nanometers in RMS, also with very good surface roughness. So we are now in the process of going to the replication of this to create the lenses. That is going to be done by SUS micro-optics. And I hope that in the next months, we'll see results of this. This is proof of concept in manufacturing. And well, to finish with the challenges, I'm going to talk about providing accommodation in headsets. So we mentioned before this conflict between vergence accommodation. And what happens in actual present headsets is that the lenses are creating a virtual image at a certain distance where the eye lenses accommodate. But this accommodation distance is different from the verged distance when the virtual object is far from this plane. So there is this mismatch that, of course, it does not occur in the real operation. When you have a mismatch that is small, is okay. Our brain can support it. But if it becomes too big, what happens is that our brain finally, gets tired. You have cyber sickness or dizziness, or even you have double image or blurring when it's too aggressive. So it's something that for the future, many groups of research and companies are working to solve. So you can see here, for instance, this vergence accommodation for a single, for the virtual plane located at 2 meters, that is calculated in diopters, so in meters to the -1. So if you consider that you can allow for vergence accommodation conflict of half a diopter with this design, that means that you will be in a comfort zone down to 1 meter from infinity. But if you go closer to this, for instance, you try to read a book in virtual reality, you might find problems because it's the vergence accommodation conflict is too high. So let's present several strategies that have been followed, let's say, rather recently. One of them is multifocal and pioneer work done by Jenny Roland's group. Show the number of planes that is needed for having a low vergence accommodation conflict. But we are going to show here one particular case in which you have a bifocal system with 2 planes. So the idea in general is that you will have the possibility of lighting virtual pixels at different depths, depending how close they are to that plane. So for instance, in these 2 positions, you will not have any conflict, but so you can get a closer limit for a comfort zone for a given BAC value. So in this case, we can reduce, for instance, from 1 meter to 0.6 meters. Of course, if you introduce more and more planes, you can get this limit closer and closer. So let's discuss specific approaches. A basic conceptual idea would be, for instance, doing a bitmap splitting, in which these 2 displays are at a different zeta distance. This way, you will be able to lead one or other display for each pixel at pixel level to provide that bifocal solution. Another option, in this case, shown in this picture with 3 accommodation surfaces, was called a focal surface and presented by Facebook Reality Labs, in which it was used a phase modulator that was able to do in real time the change of that plane, focal plane, into a shape. So you could follow with the plane the shape of the 3D scene. Even with only a single plane, you can get good results in this case. And it's a more advanced multifocal in the sense that they are not planes, but surfaces that you can dynamically change. Another approach, also by the same authors, corresponds to the use of polarization lenses in the system of the pancake architecture. So these polarization lenses are lenses which have two possible focal lengths associated to the polarization that is impinging on them, the circular polarization, and with the help of switchable half-wave plates, you can commute if one is active or not. So in this pancake configuration, introduce a sandwich that is split here, so they could be changing different combinations to achieve 64-bit planes. So they can move the full plane, not the surface, in this case a plane, in 64 steps. So in reality, this is close to a continuous movement, which is what we call in the next section a varifocal. But in this case, is with no moving parts, it's just electronically controlled. Notice the difference between this approach and this other approach here, because this we are moving completely the plane, so we are not providing a pixel level accommodation, but just if the content requires that most objects are close, like reading a book, you can move the whole plane. Of course, it also serves to compensate for myopia correction of the users. Let's go to the next one, which is varifocal, in which a first concept to achieve it would be just to display continuously to shift continuously the display on axis. For instance, if you move it to this other position, the virtual plane will get closer. And this is what was proposed by Oculus in the half-dome prototype, moving with actuators in the zeta direction, the twice independently, to be able to produce these shifts. It has been also another approach proposed by Adlens using motorized Albers lenses that with lateral movements are also able to move continuously the full plane as the other case. And these previous strategies, the multifocal and the varifocal, are producing alleviating divergence accommodation mismatch, but they are not perfectly solving it. The strategy that is trying to make a perfect correction of divergence accommodation mismatch, one of them, is what is called light fields, in which what you control in the system, or you try to control, is to control the luminance of light rays that depend not only on position, but also on direction. So with those two reference planes, what we would like is to fix in our system the function of the luminance of the four variable of the two planes. In reality, because we work with pixelated devices, so it's discretized, when we talk about the ray, we are talking in reality about the ray pencil, which are all the rays that go across those two surfaces. One way to do this that was proposed by Juan and Weinstein is to use two stack displays in which this one is the emitting one with a backlight on it, and this other one is just a transmissive. So the virtual images are shown here. So all the pencils of rays are defined by the pixels of these two virtual images. So these are the two reference planes. Of course, you don't have the degrees of freedom to fix a four-dimensional function. In this case, what you have is two-dimensional functions, and they tackle the problem of with an approximation method using a factored expression of that luminance. And another approach to do the light field is what we presented before by Landman and NVIDIA and Lübke, that is using a lens array with a display. So the pencils are now defined by the lenslet arrays, each one of them, of the units, and the pixels of the virtual image. So these are now the two reference planes defined in the pencils, and is the light field that I referred before. So we have been working on this issue at Limbach too, and we have conceived what we call human vision adapted light fields. And these are based in three key elements. First, we have identified the pixels that provide accommodation, and we have defined what is the best density of those pencils in two reference planes. And this way we can reduce dramatically the number of pencils that we used. And this is an example in which we are using these two reference planes. In this case, we change the density of pencils in particular in this one, but it can be done in the other. And this is a particular way to provide such kind of light fields. And when to finish, just as a summary, we have seen the VR optical design faces multiple challenges. We need to increase resolution, decrease the size and weight. We would like also to increase the field of view, to keep the efficiency high, and to minimize divergence and accommodation mismatch. And new optical technologies are coming to address them. Particular, for instance, using dual displays and foveation, also with the help of the eye tracking, using multi-channel or folded optics, and with a multifocal, varifocal, and light field approaches. So with this, I finished the presentation. I would like first, last to thank all my coworkers at Limbach that are behind all our progress during this year developing our technologies, and also some public institutions that have supported part of our work. So that's it, and thank you for your attention, and I'm open to your questions. So Joel, is your time.
Okay, thank you, Dr. Benitez. We now have time for a few questions. Attendees, if you haven't already, you can type a question for us into the chat box on your screen. And with that, we'll start with the first question here. Just a quick second here. First question, what materials are typically used for the Fresnel and pancake optics?
In the case of the Fresnel, usual materials are, for instance, Zeonec type plastics, and also PMMA could be used, although it's not that adequate for coatings. And in the case of pancake optics, as I mentioned before, it was commonly used glass, but now it's being avoided. So the companies are using low birefringence plastics, and there are basically two in the area that are with good performance, but in general it's a technology that is difficult to make, and the two belong to families of the PMA and the APL. So those are the basic possibilities at this moment, but it's probably that is going to grow in the future because is research going on to improve that.
Excellent. Do people with myopia have distortion with the freeform multi-channel optics?
Not, not because of the myopia. In general, what you can do, what you do when you do the mapping correction is to adjust the mapping function that is able to merge the images. It's true that in a very strong case of myopia, you will need to correct the mappings. But notice that there are two situations. One in which you incorporate the myopia correction into the optics, like in the case of the Huawei pancake. And in that case, because you are going to change something, for instance, to move a lens or to move the display, you can just change the mapping for the myopia correction. And the other situation is in which the user is going to wear the glasses in front of the optics. And in that case, the user with the eye and the glasses becomes exactly the same as a normal user, apart from the overall different distortion. But so telling it shorter is not an issue, the myopia.
Thank you. What material is used for the replication of trenza? Which requirements are important for the replication process?
Well, the trends are there are several technologies that can be used to make those type of mini lenses. One of them is based on UV curing of polymer resins on glass substrate. That is the one that is going to be used by SUS Micro-Optics. And the requirements is that you can have a very good replication of it by having low shrinkage, and also control on the iterations if you need to do it on the mold. But there are also other possibilities, like using thermal processes of hot embossing on sheets to produce the shape of those lenses. And in that case, the materials you use may be, for instance, PC or PMMA.
Thank you. Next question. Let's see here. You talked about a device that is useful in myopia. Glaucoma is another disease of the eye that involves a decrease in the visual field that the eye is capable of. Could a VR-based device correct this deficiency? Is there multidisciplinary research to find a solution on this topic?
Can you repeat the question? Sorry.
Sure. You talked about a device that is useful in myopia. Glaucoma is another disease of the eye that involves a decrease in the visual field.
Oh.
Could a VR-based device correct this deficiency? Is there multidisciplinary research to find a solution on this topic?
I'm not familiar with the details of the glaucoma disease, so I cannot say. I have not studied it. If that is a solution, I'm sorry, I cannot answer that properly. But hopefully there is. But I'm not qualified to answer.
Okay. Can you explain some more about how the passive eye tracking works?
It's not passive eye tracking. When I mentioned the passive foveal super resolution, it's just that what we do is that we guarantee that the pixels has the maximum acuity when you are gazing them, that when you are not gazing, and we take those degrees of freedom to optimize our system. But it's not a passive tracking, it's the fact that our design has embedded in it the fact that the clarity or the acuity that you can, how clear you can see a part of the image is now dependent on if you are gazing it or not. But that's embedded in the optics. There is no eye tracking in that.
Okay. Do you believe VR or AR will be as common as smartphones or optical glasses?
Yeah, good question. I think that I don't know if that's common, but I'm quite certain that when we reach the good size and resolution, the areas of applications are going to expand more and more. So now the most used one is gaming, but it's going to invade many other areas of application, like for instance virtual office. So you have sunglasses like headsets that you can put and work on an office with many screens, not limited to them, and not to carry a big screen, but just to carry your your glasses. So, but probably that will need a better form factor and a higher resolution, but it will come. I don't think it's going to substitute the cell phone, for instance, but certainly will become a much wider spread, I think.
Excellent. Here, just a moment. Is there a required RMS for the lenses, and is it possible to produce it easily?
If the question refers, when you say RMS, it probably refers to the surface quality. Probably yes, I guess. So in general, for all imaging applications, you require a surface reproduction, which is very good compared to other manufacturing processes of other parts, let's say, non-optical. So the typical optical accuracy that is required for optical parts made, for instance, by injection molding in plastic is in the range of 10 microns peak to valley. Of course, it depends on many things, depending if it's refractive or reflective. It depends on the diameter, etc. But that's a kind of a ballpark number to start with. So it doesn't mean that you will always need that accuracy. It depends on the surface, the power of the surface, etc. And you have to do a detailed tolerance analysis to see where you can allow further deviations or not. But in general, it's an accurate part that needs to be done by a good optical plastic injection manufacturer.
Sure. Has the design of stacking many layers of transmissive displays in order to simulate depth with multiple layers of images been abandoned?
I mean, multifocal displays is something that has been around, and if he's referring to the one making light fields, the stack displays, which is a recent one, in that case, it's a light field, it's not multifocal. It's not been applied at this moment, to my knowledge. I mean, to get close to commercial, but I wouldn't say it's abandoned. In general, it's one of the paths that that may be being followed. When I say this is because in reality, most companies have their internal research and they are not publishing it. So we don't know what's going on in many of them.
Okay. Are standard injected molded optical components accurate enough to produce display surfaces?
When I say display surfaces, I guess he's referring to optical surface for virtual reality. And the answer is, I would say, it's not, let's say, standard, but it's precision injection molding. It doesn't mean that you need a very complicated process, in the sense that maybe you don't need to go to injection compression, maybe you don't need to go to isothermal cooling of the mold and all the more advanced techniques. Usually it's not needed, depend on the piece. And if he is referring to he or she referring to the question of the display itself, making curved displays is on polymer substrates is a different area, and it's not to be discussed here, and I'm not an expert either.
Sure. In a pancake lens, what's the half mirror usually made of? Is it made of a metal material?
Yeah, I mean, you can do it. It's metal material. Yeah. It can, yeah, it can be done also in principle with multi-layer, but.
Sure. Are you also doing work with augmented reality? Are the optical challenges overlapping or quite different?
So yeah, we are also actively working in augmented reality or mixed reality, and the challenges, as was mentioned, they are different in principle. In general, augmented reality is if you are using the approach of optical see-through, so the optics has to be transparent, that's a very big constraint in the global architecture of the design. And then it's very common that the field of view is not as wide as the case of virtual reality. And the problem, globally speaking, is more complex because of that see-through condition. Apart from that, there is the other option that I mentioned in the talk, the one followed by links, which is using video see-through. If you use video see-through or video pass-through, you have some advantages and some disadvantages with respect to the optical see-through, but it becomes a problem of making a virtual reality glasses and now cameras and the processing of putting them inside. There are challenges to improve and so, but that is closer to the design problems that we have in virtual reality.
Okay, we're a little bit past the hour, so we're going to, this will be our last question today.
Okay.
What are the smallest structure sizes which have to be realized within your freeform lens designs?
In the Trenza ones, the size of the lenses is in the millimeter range. So we are not in the micro lens size, but in the mini lens size.
Excellent. Thank you, everyone. If you would like a copy of the presentation or have another question for us, please contact us at webinar@photonics.com. That's WEBINAR @photonics.com. A recording of this webinar will be available next week, and you will receive a link to that recording by email. So please keep an eye out for that in your inbox. I would like to thank our presenter again, Dr. Pablo Benitez, CTO of Limbac and professor at the Technical University of Madrid, and everybody here for participating in Virtual Reality Optics Present and Future, hosted by Photonics Media. Goodbye, and with that, I'll close the webinar. Thank you, everyone. Thank you, Pablo.
Thank you.
Thanks.